Hello and welcome back to another LeetCode problem. Today we're looking at 1039, minimum score triangulation of polygon. I have not solved this one before, so yeah, I kind of want to try it. So let's see what we have here. We have a convex n-sided polygon where each vertex has an integer value. You are given an integer array of values where the ith value is the value of the ith vertex in clockwise order. Okay. So we have so it's like a circle, like a circle consisting of points, I suppose. And polygon triangulation is a process where you divide a polygon into a set of triangles, and the vertices of each triangle must also be vertices of the original polygon. Note that no other shapes other than triangles are allowed in the division. This process will result in n-2 triangles. Why n-2? Let's say if we have 3, then it's only, yeah, if we have 3 vertices, then it's 1 triangle, so it's n-2. If we have a 4, like a square, we can only divide it once, and then we have 2 triangles. Okay, guess that makes sense. You will triangulate the polygon. For each triangle, the weight of the triangle is the product of the values of its vertices. The total score of the triangulation is the sum of these weights over all triangles. Okay. Return the minimum possible score that you can achieve with some triangulation of the polygon. So that means we have to compute all possible triangulations and then find the one that has the minimum score, I guess. Constraints. Okay, so the values of the vertices are between 1 and 100. None of them are 0. That's good. And the constraints is we have at least 3 vertices. So we can always form at least 1 triangle. Okay, that's cool. Okay, let's look at an example. First one, 3 vertices, output 6. The polygon is already triangulated because, yeah, we cannot create smaller triangles from 3 points. And the score of the only triangle is 6, so that's a product of 1, 2, and 3. Cool. Example 2. Now we have 4 values. Excuse me. There are 2 triangulations with possible scores. Let's try to come up with that ourselves. So, I guess I could pick the first 3 vertices and form a triangle. And then I have to pick the other 2 vertices that connect with 5 to form a triangle. So that would be, so since they are in clockwise order, so if I pick the first 3, so that's like the example with the rectangle or the square. We pick 3, 7, 4. So now we know that we have to pick 5. So, but we also have to connect it to its neighbors, right? That'll be 4, 5, and 3. So see 3, 7. Why does it pick 3, 7, 5? Oh, is it that they pick those 3? Those, and then we would have to pick 7, 4, 5. But it's a weird order, isn't it? Weird ordering here. The ordering isn't the same as in the input values array, so that's kind of confusing. Okay, that's one possible triangulation. The other one is, I suppose that's exactly the one that I was going for. That's 3, 7, and 4, and then 4, 5, and 3, just in a different order. So this is now sorted order. This is not sorted order. Weird. Okay, yeah, but I think we get the idea. And then for each of these triangulations, we have to compute the scores, right? And to return the minimum. Okay, let's see if we see a pattern here. So now we have 6 vertices. So, okay, they only give one minimum one. Let's try to see how they pick the minimum. So they have 1, 1, 3, and 1, 1, 4. So this would be 1, 1, 3. This would be 1, 1, 4. So now there's only one overlapping vertex, which means the last one would have to be 1, 1, 5. And okay, and then 1, 1, 1. Okay, that doesn't make sense. Well, I guess that's correct, but how they pick them doesn't make sense to me. Would be nice to see, how they pick all the other ones and compute their scores. But that means probably that a linear approach isn't really going to work that well. We just pick consecutive vertices. So if we have a polygon, we just pick adjacent vertices. It becomes like a clamshell shape where we have lots of edges coming from one of the nodes, slicing the polygon into strips, basically. So that would be one way to slice and dice it. But then there are of course others, right? And we also can't just pick a different starting node every time and do the same clamshell slicing. I don't know what to do here. Maybe let's look at the hint. Without loss of generality, there's a triangle that uses adjacent vertices a0 and an minus 1, where an is the length. Depending on your choice of k, what k, of it, this breaks down the triangulation into two subproblems. Oh, all right. Okay. Well, yeah, we could use a divide and conquer approach. We could say we have our polygon, our circle, and we just slice it in one way. And then we have two subproblems, and they're still in clockwise order, and they're still convex. So we could, recursively divide the remaining polygons into triangles and compute the weight once we broke each section down into only 3 vertices. Only thing we would have to do is we would have to iterate over where we make the cut. So it's a lot like merge sort, right? Kind of a divide and conquer. So we're probably going to need a helper method for the recursion. And because we don't want to copy the values of the array, we're just going to pass it maybe the starting and the end index on the vertices to operate on. We have a left and a right. And we have to call this helper function. And maybe we make the helper function return the minimum value. And helper left would be 0. And length of values would be right. So right would be exclusive. We could also do -1, then the right is inclusive. But let's make it, how should we do this? Yeah, let's make it exclusive. You know, sometimes it's less hassle to do it inclusive than exclusive. It's worth to try maybe both implementations. So, okay. Now, okay, but there are so many different ways to slice this polygon. We're probably going to run into a case where we have to recompute something that we already computed. So maybe we would have to put the results into a cache, right? Something like a cache that maps the parameters to the value that we computed. Maybe. Maybe we need to do it, but let's keep that idea for in a moment. All right, cool. So, well, what do we do now? Well, what is the edge case where we should terminate the recursion? If we have less than 2 vertices in that range, then we can compute a score, right? So it would be 0. Let's think about it. Should it be 0? It probably should be 0, similar to this example. Where, well, if we, yeah, because if it is 0, I'm just thinking, because if we return a 0, we need to be careful that 0 doesn't become our minimum value. But let's for now just return 0. So, well, how many nodes do we have here? Well, num vertices. That would be a right minus left plus 1. Because if left and right are 0 or the same, this would be 0. So we have to increase it by 1. That means 1 vertex. And then we do if num vertices is smaller than 3, we're just going to return our 0. If num vertices is equal to 3, that's the other case, then we just need to multiply its values for the score, right? So we're just going to return values. Left and well, left times left plus 1 and times, let's think about this. The third vertex doesn't have to be, do they always have to be adjacent? But this would be the right one or value plus 2. Right. Yeah. Would we ever run into a case where we have to compute the score of non-adjacent vertices? Yes, we will. But that will occur during the slicing, right? So when we do a slice in the middle, I think that's when we will run into that case. So here I think we should be safe. Yeah, this is not an easy problem. Okay, and now that we've handled those edge cases, we will deal with, well, making the big slice or the different slices through our polygon or subpolygon. So we'll have, I guess, a mid, we could call it mid, in range left, and we already picked left as one of the slicing points. And we're going to iterate until we reach the right value. And so what we're doing is we are slicing from left to mid. That's where we're going to do the slice. And doing +1 here doesn't change anything, so we'll keep it like that. And now the score is, what is the score? Well, the first triangle that we have is values, because at left, right, that's one of the points we start to slice from, with values mid times values right. So yeah, so this is to pick the third point. Yeah, that's actually why +1 wouldn't work here. So that is what we do. So we create a new triangle, but now we have to take care of, let me think. Yeah, so if we enter our helper, we start with 2 vertices, the start and basically the end of our polygon in the vertices array. And now we pick the third. So that is, we're forming a triangle while we do this. Now we formed one triangle, and that means that now we have to form a we have to compute the minimum, what is called minimal possible triangulation for the remaining triangles. And the remaining triangles will start at left +1 and go to mid, right, between that. And the other one is between mid and right. And actually, yeah, we have to pick left again. So left and mid are now 2 set points for the next triangulation, and mid and right are also 2 set points for the triangulation. But this will be now handled in the recursion. So we say score plus equals helper left to mid, and the other one is score plus equals helper mid to right. Yeah, that makes sense. So picking the inclusive right end here was the right choice, so that we don't have to do here +1 or something here. Cool. But now we have to compute the minimum score. So this will compute all of the scores of all possible triangulations inside whatever this polygon is. So we have to find the minimum, right? Min score, and maybe set that to float infinity so that we don't run into the zeros. And then we just do min score as minimum of that plus our current score. And then in the end, we just return our min score. Yes. Let me just think about this. So left and right. I'm just thinking about this case. It must be that because left and right are consecutive numbers. And so that must work. I'm just, yeah. Yeah. I'll just leave it at that. We'll see when I step through the debugger if all of that is correct. Oops. Okay, cool. So that should be that. So if we calculate this score, it's guaranteed to be not 0. Then we go into the helpers, etc., etc. If we run into a triangle, an exact triangle that exists, then we return its weight. And the case where we run into where the number of vertices is smaller than 3, that is actually, that can only happen if our length value is smaller than 3. Because otherwise it means we have already formed a triangle with left and right and some other point. So when we start to go into our recursion, we're actually looking at combinations of vertices that are already part of a triangle, and we don't care about them. So that's why return 0 should work here as well. Cool. So now the problem of recomputing values for the triangulation between left and right. Since we're doing all this iteration, you can easily see that we might make the same slice between two vertices many times over. So we probably need some kind of caching mechanism. And so we could use a hash map for that. And we could just compute the key here and we make it a tuple, because that can be used as a key in a hash map. If key not in cache, then we'll actually need to compute the key. And we will do something like this. Cache key as the minimum score, and then we just return cache key here. So that would give us an easy way to do that. Yeah. Let me think about this. Yes, because we are computing the minimum possible triangulation of a polygon for this problem from left to right. It is guaranteed that when we call this again, it's not going to change its value. So I'm fairly confident that that should be it. Let's step through this example. So we have input 1, 2, 3. Our left is going to be 0. Our right is going to be 2, right? So index 0, 1, 2. Our key is not in the cache yet. So what we do is we compute the number of vertices. So it's 2 minus 0 plus 1. So it's actually we have 3 vertices, which is exactly this edge case. And then we just return the... Oh, I see. Now, left plus 2 and right. So let's say if left... What if left was pointing at 1? Well, then right couldn't point at 0. Okay, so that should be fine. Yeah, then we just compute the product of the consecutive values, which would be 6. And we just, we can't return 6 here. We should put it in our key cache, right? Equals that. We put this, all of that into an if else, so our min score would be that, and otherwise equals this. Yeah, so now it's cleaner. So the min score gets computed at that, then we put it into our cache, and we return the value 6. Okay, so this example works. Now let's pick the next one. So again, we start with left 0, right is being S3, but the number of vertices is of course 4. So we're going to enter this case. The minimum score is set to infinity, and we're now going to iterate over the mid. So we're starting at index 0 plus 1. So 1, 2. Well, mid is going to assume the values 1 and 2, but not 3, because that's an exclusive, not included in the range. So first what we do is we compute the value of left as 3 times 7 times 5. 3, 7, oh, so now the order is actually, that makes sense, 3, 7, 5. But we're going to add the scores of the sub section. So we divide now. We go from index 0 to 1. That is the case where the number of vertices is small. So this is actually 0 in this example. And we go from index 1 to index 3. So 3 minus 1 is 2 plus 1 is 3. So that is exactly this case. So our left would be our new mid. So that is actually the 7. 7, 4, 5. 4, 5, 7. Yeah, that's this case. So we multiply that, we add them, and we add them to the score. So our minimum score is now the minimum between minus infinity and this 245. Cool. Now we return, and we continue iterating with our mid, right? So mid was 1, and now mid is 2. So we're computing the score left times mid times right. So that will be 3 times 4 times 5. That's exactly this expression. And then we do the recursion from left to mid. So that would be from left to mid. So in our next recursion step, left becomes stays 0 and right becomes 2. And that's this case where we have 3. So we now have 3 times 7 times 4 in a different order here, which is that value. Yeah, and the other case is again smaller than 3. So I think that should work. Let's put it to the test. And it's accepted. Very nice. Let's see if it passes all of the tests. Okay, cool. So what I skipped was the runtime analysis. Well, I already hinted that it's a divide and conquer approach. So we're going to have a number of recursive steps here. And we are going to iterate over, in each step, we're going to iterate over all of the vertices at the current split. So we have, let's say we have k recursive steps. And in each step, we're still iterating over all of the nodes, right? If we split something in half, we iterate all of the nodes with our mid variable in that part, but also in that part. And if we split it even further, we still do the same. In every split, we still iterate over all of the nodes. So they sum up to n, right? K recursive steps and O of n operations per recursive step, right? Right, so that's going to be our time complexity. So we have, how many recursive steps do we have? Well, since we're caching things, we're significantly reducing our runtime. Just trying to get it together now. So we're guaranteed to never compute the same sub interval again. So the number of different combinations of left to right interval, how many is that? Well, it's basically equivalent to having 2 for loops. So the first one goes from 0 to n, and the second one goes from I to n, right? So I think it's an O of n squared time, if I'm not mistaken. And we're going to have O of, it depends on how many unique splits we can have. And I think maybe O of n base, because we can make n different, well, n minus 2 different cuts in the first example, but then in every sub polygon, we can do that again as well, right? When we combine the sub. So I think that's the space and time complexity. I'm not 100% sure, so maybe we should have a look at some of the solutions. Maybe Python one. Python, top-bound, dynamic programming. Oh, nice. So here's some graphics. Yeah, so this is basically what we do inside our our loop here. Pick 2, and then we iterate over all of the different ways to slice it. So that's the same approach. Does it give a... Okay. So he also has a base case. I don't know what that case is. But he then iterates over all of those things as well. I don't know if that is comparable to our base case here. But also calculates the value like we did. So this seems very similar. So what is that runtime analysis? There's no time complexity here. So it's O of n cubed, and space complexity is O of n squared. Oh, yeah, because I forgot the cache. So we're still storing all combinations of pointers in the cache. So yeah, that's why our cache is also going to be O of n squared space. But why is the complexity O of n cubed? We have n squared subproblems. Oh yeah, and for each subproblem we have to try O of n possible middle vertices. Okay, so yeah, so my reasoning was a little off here. So it's actually O of n cubed and O of n squared time. Yes, I have to think about it a little bit more. But yeah, you're welcome to do the same. Thanks for watching, and happy implementing.